Okay, so welcome. This is something a bit new. I'm here with my friend Avi, and what we're going to do is learn Lean 4, which is a programming language.
Yeah, and some of the interesting things about Lean 4 is it is like known as a theorem proving language for mathematics, but it also is a very capable functional programming language that has a really rich type system, including dependent types. So I think Richard and I in the past have both been interested in programming with languages and dependent types. We tried our hand at Idris several years ago, and now it seems as though Lean 4 is kind of one of those programming languages on the cutting edge of using advanced type systems, but also being a kind of semi-practical language. And so I say semi-practical because I don't think it's actually used that much, but hopefully it will be in the future more. Yeah.
Yeah, so you're going to bring me into the modern age of programming, right, Avi? I'll get out of my
Oh,
using
yeah.
pen and
And just to
paper.
be clear, I'm also a total newbie when it comes to programming in Lean 4. So we're going to be learning this together. And but yeah, so to start, we're going to install the language. So we're assuming you have VS Code already installed on your system, and if you don't, you can easily find that. Just Google VS Code and install that.
Yeah. So, like, basically, just to say a bit of background, me and Avi have been communicating about different interests in maths and philosophy and different stuff for a few years. People who follow this channel will know that I'm pretty into category theory and formal mathematics, and Avi's very interested in those things as well as other philosophical things. So I shall put in some links of the description so you can follow more of the stuff that he's into as well. And what we want to do with this video is like to basically, we both want to learn lean. We both, well, I don't know about you, Avi. I'm pretty rusty on my type theory. Like, I
Mhm.
haven't done much of it for a while. So we wanted to try and make something that um, anyone can follow, and we'll try and make it some kind of dialogue thing with hilarious jokes and that kind of
Oh
stuff.
yeah, we're regular comedians.
Absolutely, yeah. And so it should be like highly entertaining, but also, we want to try and put content in that people can follow along with. So yeah, do you have more to add about
Yeah,
the
well, I was
intentions?
just noticing, when I was searching on YouTube for videos on Lean, that they're all kind of very high level academic videos, very advanced seeming and kind of intimidating to me as a regular programmer. And so I think like, yeah, there would be kind of nice to have some content out there for people who just want to learn to program in Lean, and maybe we'll eventually get to some of the theorem proving stuff, but kind of starting with the programming side. Um, yeah.
Yeah, yeah, and it's kind of topical, right? Because there's all this stuff with like Chat GPT. Is that connecting with Lean, or is that maybe
I
not?
don't know. Maybe not, this might. I
We've got to make
well,
it sound like this is.
I mean, I don't think it is yet, but actually, I did read that like Lean is a programming language developed by Microsoft, by like Microsoft Research,
Mhm.
and they are trying to use it now to train AI models to do mathematical proofs,
Right.
right? So they haven't, I think, gone that far with that yet, but I do think like in the future we'll have sort of Copilot or ChatGPT like things, but they are going to be actually rigorously proving
But it's
things.
not like a thing yet.
It's not, it doesn't exist yet, but
Right. Yeah, because
this is recorded in 2023. By the time somebody's listening to this 6 months later, probably it'll exist, right? Yeah,
Skynet will have taken over by now. Yeah.
yeah.
But yeah, it's like because there's like Lean and Agda and Idris and COQ as I call it, and I mean it seems like a matter of time until someone plugs up some Chat
Yeah.
GPT thing to one of them and mathematics just goes. Shh. But I guess it
And
hasn't happened yet.
one of the things about Lean is it has the largest library of mathematics. It's called MathLib. And basically that has like people have programmed in like a ton of mathematical theorems, still far from all of them because the universe of mathematical theorems is so huge, but there's actually a lot of formalized mathematics that's already been programmed. So that could be used to train a model in
Yeah.
how to do this kind of stuff.
So maybe lean is a good candidate. But we're going to be using lean 4. Is that stuff still accessible to us? Just something I wanted
Yeah,
to.
so at the moment, I believe the community is still in the process of migrating from Lean 3 to
Ah,
Lean 4. So there are like some ports of the MathLib library, but the primary MathLib library is still in Lean 3. However, like they definitely are moving towards
so the
bringing it
intention
in.
is to make lean 4
Yeah,
so it can run the old stuff.
exactly. Yeah, they're going to have an automated way of kind of porting over the library, but to do that, they have to like make sure they have all of the like, well, this is getting a little technical, but all the tactics and things that people have programmed in to prove things in the math library, like they have to make Lean 4 versions of those. So that's what's the main bottleneck, as I understand it.
Okay.
Yeah.
Well, in the hope that we're not learning a redundant language, like
No, no. I mean,
let's.
so just I'll tell you I mean, I think the features of Lean 4 over Lean 3, it has a lot nicer syntax, at least for me, like coming from the TypeScript, JavaScript world, it feels a lot more familiar.
Mhm.
Um, it also has like a better compiler, and like you can basically like it's basically able to make more efficient programs. So you can write something using this functional programming style, but it will still execute in a way that's closer to, say, writing it in a system programming language like C++. So you can sort of write more serious software in it, supposedly. I haven't tested that myself, obviously, but that's what I read. Um, and it's also got like cool things like metaprogramming and being able to write macros, which are basically programs to write programs. And you can write domain specific languages by like extending the syntax of the language. So yeah, it's got like a lot of interesting features. I mean, those are more advanced, but to get there, we have to first learn the basics. So
Right, right, right. So I guess then we're going to start from the beginning, I suppose, and we'll try and explain things from a very basic level. This is the intention. So, like, um, yeah, there won't be any sort of prerequisites. You don't have to know type theory or category theory or anything to follow along with this. And I guess the first thing we're going to do is set the thing up. So I'm using VS Code here, and Avi's also using it, and we're going to be sort of using VS Code and getting Lean running with that. All right then.
all right.
So we're going to
So
set up
yeah,
Lean. So what do we
great.
do, Avi?
Okay, so in your VS Code, start by going to the extensions thing and just search
Is
for Lean
that's this
4.
one, right?
Yeah,
Uh, and search for what?
Lean 4. I think all one word, like with the number 4. Yeah, there it is. Okay, and just click install there.
So I haven't installed any files other than this. So this will do
Yeah,
it all,
that's
right?
right. Well, this and then you'll get one more prompt, which we'll see. Yeah.
Wow. Okay.
Okay, so now we're going to go to our to this file we started here, um, and oops.
So for people following along, they could just open any file in VS Code, right?
Yeah, so we have this evaluating expressions file, which is just the name of the first section of the textbook that we're going to be following. We'll put the link to that textbook also in the description. And
Yeah.
so if you go to if you go down to the lower right corner where it says plain text there,
Hmm. But just for someone following along, they can just open any file and follow along, right?
so well, I mean we're trying, so go to evaluating expressions and click on plain text in the lower right corner. Yeah, and now start typing lean. There you go. Now select lean 4, which is the second one there. Okay.
Ah.
And now you get this pop up. Okay. And it says install lean using elan. So click on that. That should install the actual language for you.
So they could do similar if they would just open a general text file And again, they'd
Yeah.
click the plain text at the
This
bottom
is just
right.
this currently is an untyped file.
Yeah,
Yeah.
got it. So now this is doing some installing stuff.
Yeah, and you want to leave this terminal. You can also
Ludicrous.
close your extensions tab now.
So
Just
I
click
click
on
on
it.
those blocks, I guess.
Yeah,
There we go.
there you go. And maybe make your text a bit bigger because it's a little small. So Control plus. Click on the main window and then click Control plus.
Hold Control and press plus.
Yep.
Oh, okay.
Yeah. Yeah, that's okay. So go into this evaluating expressions file and just rename it .lean. Yeah, and now right click on that evaluating expressions, rename, and it just add .lean at the end of it.
Dot what?
Lean. Yep. Okay, now you can close this tab again.
Right, so anyone following along will have to do this as well, right?
Well, yeah, and when you create the file, you could just have made that as your file name to begin with.
So just to test it, if we want to make a new one, we go new file, and now I can file type, so I can put in lean, and now it says create new file lean, so it knows what that means presumably. So I click it, and now I have to give it a name, so I'll call it rich2. Rich2.lean?
Mm-hmm.
Should it be .lean?
Yep.
I guess. Okay. And now it knows this is lean, presumably.
Should, yeah.
Okay. So we could work in this file, but we've already created this other one that has a more appropriate name. So let's work in this evaluating expressions.lean.
Okay. So,
and what's this like window thing on the right here?
So this is kind of your info view, and that tells you basically all the stuff you need to know about your, like that's where you get your type checking and your evaluation. So evaluation is basically like running the program internally to tell you like what it comes out to.
Okay.
So what do you, so yeah, so, and when you get, now I just pasted that in, that comes from the quick start guide, and which will also link, we should also link to in the description. But basically that says, that's a special thing, you know, it's got a lean object and a version string. And so it just printed the version of lean that you installed.
So that printed this.
Yeah, 4.1.0. So that's just to confirm that your installation of lean was successful.
Did you have to like press run, or does it just like run it automatically?
Because the eval, the hash symbol eval is like a special you know, command word that tells it like evaluate this line.
Right.
And so that I forget what that's called. That eval basically is like saying like run this line of code, and it will also run any other code that's dependent, that line of code depends on.
I'm sure this isn't going to work, but if I go eval 1 + 1, hey, it does work. Oh my god,
it does work.
It knows how to do arithmetic. That's brilliant.
You have a calculator, yeah.
And it's now it's not showing the lean version anymore, so presumably it just runs the last eval.
It's just whatever line your cursor's on. So if you move your cursor up to the previous line, you'll see it.
Oh wow, it's a calculator and a printer. Amazing. Right.
Yeah. So, okay, so now we can actually get started with the actual book, right?
Yeah. So we're following along with. Oh God. Okay. Yeah. Just say what it is, because maybe I can show it. So we're following this, right? It's
yeah. It's
functional programming in Lean. Right. I'm going to get off that now, otherwise I'm not going to be showing the right things on the screen. There we go.
Yeah, and it's by David Thrain Christensen.
Right.
And yeah, so this was, yeah. Okay, so you just actually did the first example of code, which is like evaling just basic arithmetic. So you can try it out with whatever kind of arithmetic expression.
Okay, so we can do adding, timesings like this, presumably.
Yeah.
Let's see if we can do powers. Yeah.
Yeah, yeah.
Okay.
So you kind of get what you'd expect in terms of basic math. Um, and now, what if you did like instead of eval, change that to check, like hashtag check, right? So now
Ah.
instead of showing you what the result of taking the 2 to the 3 is, it says that that's a natural number.
Okay. So now we're getting into a little bit of type theory-ish thing. So this, how would you pass this? I would pass this as 2 to the power of 3 has type natural number.
Yeah,
Do you
and
kind of agree with that?
yeah, that's right. So on the left there is the value, which is it's not actually evaluating that expression. It's just showing you the expression, but it's still kind of at the value level.
Hmm.
Just for listeners who don't know type theory, in type theory, there's the idea of types and values, and a value is basically like think of it as the instance of a type. So if I have a type of natural numbers, then anything which is a natural number, like 1, 2, 3, 1,000, 0, those are all natural numbers, right? So um, expressions like 2 to the 3, even though we haven't done the computation to know what that number actually is yet, um, it still knows that it's a natural number. And that's one of the cool things about types is you can know what the type of something is even before you've done the computation.
Yeah, yeah. And I sometimes take a sort of simple-minded view of type theory, which is to mean that, which is to say that such as nats would represent like a set, like the set of natural numbers. And
Yeah,
then this kind of colon here could almost be read like in. So 2 to the power of
yeah,
3 is a member of the set of natural numbers, although,
yeah,
you know, one of the points of type theory is to be a bit more sophisticated than that. But usually
yeah,
thinking of types as sets, and when you have a value of a type, it's like a member of a set, you can
yeah,
get pretty far with that kind of
yeah, yeah, exactly.
thinking.
It's just like yeah, when you get into the more complex types, that starts to break down a bit. But for this type of thing where it's just like, yeah, it is a set, it is a set of natural numbers. But I guess you can always think of them as some sort of set if you want to. But yeah,
Right.
so let's keep going with the evaluation of expressions. So um, let's try this. Okay, I'll paste in another example from the book. So
Hello, Lean.
yeah, so
Uh,
you
it's a
can
bit too, it's not visible. Like,
Oh, okay. Maybe set your
can
go.
I pull
So
that a bit that way?
you got to set VS Code to word wrap.
Oh, right.
So or to line wrap. Do a control. Now I'm switching between Mac and PC, so I forget what the keyboard shortcut is to open the command palette on.
So I go to settings.
Hang on.
You uh, programming people with all your keyboard shortcuts. It's hard to keep up.
Control Shift P.
Well, type in word wrap.
Yeah, or line wrap, or just wrap. Just try wrap. Toggle word wrap. Yeah, that's it. I guess it is called word wrap. I'm not sure why. Okay, now try making it smaller. It should wrap. Yeah,
That's
there
a
we
wrap. Yeah, great.
go. Okay, so this is the first example, and you'll see here that there's an error, right? And this is because of like so in say like JavaScript or Java or many other kinds of programming languages, we wrap our arguments for a function call using these brackets here, right? So like, and then we separate our arguments with commas. But in functional programming languages like Haskell, and Lean is more based on the syntax of things like Haskell, we just apply our arguments directly like that. So we remove the brackets and the commas, and we just separate the arguments with a space. So
Ah, and
hello,
it works.
and it works, yeah. So hello is a string, Lean, this Lean exclamation mark is a string, and append is a function that takes in two strings and sticks them together.
All right, this is cool. So let me see if I can. Let's see if we can make it display what this string append is doing in a sense. So we're going to sort of, how do you say this, Avi? We're finding the type
Yeah,
of
this is the
string
type
append.
of the function string append. And this might be a little tricky for people to read, but it's basically saying that the string append takes two arguments. The first argument is a string, and the second argument is a string, and then at the end there it also returns a string. Yeah,
Okay, so let's try another one maybe. So
yeah. Okay, so let's just keep going through this textbook examples here.
uh,
So here we're going to do like a nested application of string append.
right. So which part of the book are we on now?
Same section, evaluating expressions.
Okay.
So if you put your cursor on that line, you'll see what it evaluates to.
Great oak tree.
Yeah.
Ah, okay, I see.
So you want to explain what's going on here?
Uh, yeah, I guess. I'll try and draw a picture. Okay, I'm not sure if this is easily visible. Maybe it's not going to come up very well. But it's basically doing this, right? We're calling string append with great, and then the other string is this one, which is obtained by doing string append again on oak and tree.
Yeah, that's right. So it's taking this string append is making oak tree, and then you're appending that with great. So that's because string append only takes two arguments. So this way we have to kind of do it as this nested application. That might seem kind of unwieldy. You might ask yourself, well, why not just have like any number of arguments? So I think we'll find out as we go forward that functional programming has its own way of doing these things, to sort of start with these tiny little functions that do very little, like seemingly almost nothing, but then building them up into powerful combinations of functions.
Yeah, it's a very weird process, like learning functional programming. I think at the beginning, it can seem like you're sort of tying your hands behind your back a bit for no reason. And
Yeah,
then eventually, certainly with me, I kind of got quite fond of having all these restrictions because it forces one to think in a very clear kind of way. Well, at least that's the idea. But
yeah,
yeah,
yeah. So now we're going to go on to another thing. So this is the next example in the book is, often with like languages like JavaScript or other imperative languages, no, JavaScript debatably would, but more conventional, let's say, programming languages, you have like if-else statements and things like that to control the logic of your thing, and we don't in functional languages they don't generally have like if-else blocks, because that kind of has like different sort of blocks of code that like different paths basically that the program can go down. The way you do it in a functional programming language is more like using an expression. So in some languages, they have what's called the ternary operator, where you like basically take in an input that checks if something is true or not. And if it's true, it gives one value. And if it's false, it gives a different value. So we'll show
yeah.
that.
So
Yeah.
it's like this idea that like everything's a function. Yeah, so you can
Yeah.
have like functions that can import or output booleans, like true or false values, and like an if statement, it'd be like it takes in a boolean which says, are you going to do the first thing or the second thing? And then there's a first thing and a second thing, and then it's like if you put in a true, it'll output the first thing, and if you put in a false, it'll output the second thing.
Yeah.
That's
So if you
usually.
move your cursor down now to line
Oh,
13.
we have if then else. Great. Okay.
Yeah. So what is this doing? It says if 1 is greater than 2, then yes, else no. And now when you append that with it is, you get your final answer, which is it is no. Do you see that?
Yeah, right. So um,
So if you change that condition
so we
after the
could
if to
we could
something
like pull
true,
this second part out to be a
yeah,
bit more modular.
sure.
Um, so if we just look at this, I guess we can just eval this on its own.
Hmm.
And we see that this is giving us a no
Yeah,
because here we've got like 1 greater than 2. So let's be a bit more modular about this as well. What's this doing? So eval this. Oh, so that's giving us false. So I guess
Yeah.
false, you just write false like without any speech marks or anything. It's like a primitive. I don't know
Yeah.
what you call it. Right, right.
Yeah, it's a primitive value. So if you actually checked that, you would see what the type of it
Oh,
is.
great. Okay, so let's type check it. So check false. Tell me about false. Right, so false is a Boolean. Okay, so we've got a false, and then
So
one greater
obviously,
than
if
two
and
is false,
yeah,
and then so the way this if statement will work presumably is like when this is false, it's going to output this, and when
yeah,
this is not false, when it's true, it'll
yeah.
output that.
And then let's change that expression 1 greater than 2 to something like that's true, like 2 greater than 1 or 3 greater than 2 or something.
Yes.
Okay. And yes, so you can see that now it's selected the other branch and it's selected the then rather than the else.
Right, right. And
Yeah.
then this one here will just be sort of chaining these together. So we know that the thing in the brackets at the end is going to give us a no, and then that gets appended to it is. So we get it is no.
Yep. Exactly. Okay. So we can continue on through our book. Okay, that's actually the end of the section. Oh, there's some exercises. Should we try them?
Well, let's see. Yeah, let's test ourselves. I didn't know there'd be exercises. I would have, yeah, get a better night's sleep.
Well, I mean, okay, it's so I'll just paste this in from the book. And we can comment this. Okay, so this also shows you how to do lean comments. You do 2 dashes for
And
like one.
that comments out a line, yeah?
Yeah. Okay, so it says, what are the values of the following expressions? Work them out by hand and then enter them into lean to check your work.
Oh, I didn't know we'd have to do arithmetic. Jeez.
I'm not going to work out 42 plus 19. Let's do like 10 plus 19.
Well, can't you make it a bit smaller?
All right, 10 plus 3. All right, there we go.
Come on.
Okay.
Okay, we could do this.
So, do you want to do the first one, or I'll do the
Oh,
first
the
one?
pressure, man.
Okay, I'll do the first one. So eval 10 plus 3.
14.
What do we get?
Oh, we got to put the cursor on it, right? Oh,
Yep.
13. Okay, nearly.
Whew. Okay, why don't you scroll up a bit, and then
Huh?
yeah, just get the examples at the top of the screen there.
Right. Okay.
Yeah. All right. So that worked. Hey, it can calculate numbers. All right, you do the next one.
Okay. String append A and then string append B and C. So there's no spaces, so I guess we're just going to get A, B, C. Let's see.
But we're supposed to work out what we think it should be before we do the
it'll give A, B, C, right?
Okay.
That's
yeah.
that's my that's
ABC with no spaces.
Yeah. Wow.
Yep.
Okay.
Wow, you did it.
I'm as good as lean.
Yeah, this is an important skill for programmers, is to like basically mentally simulate what the language is going to do.
Yes.
Okay, so this one is taking string append and putting A and B together, and then string append and putting C together. Oh, so it's going to be the same.
Pretty analogous to that tree thing from before, right?
Yeah. And so what this is showing is just that it doesn't matter if you append the A and the B first and then append the C, or if you append the B and the C first and then append the E, which in math terms means it's associative.
Yep.
Right? And however, notice that we did actually put this in brackets here. So even though in general we don't use brackets for arguments, we still use brackets for like grouping argument application.
Right, because we can only put 2 in, so.
Right. Well, we want to show that what we're doing here is we're applying A and B to string append. We're not applying string append as an argument to string append.
Oh, yeah. That's important. Yeah.
Yeah, because in functional programming, you can apply functions as arguments to other functions. So if we were to apply string append as an argument to string append, it would give us a type error. Why don't you just take those brackets off and we can show that.
Okay, so the way I usually think of it is like when you put brackets in a lot of places in math, it means do this first.
Yeah.
So if you
So,
imagine
well,
you're trying to,
hang on. Let's look at the error message we got there
oh,
because that's instructive.
I usually think of error messages as bad things, but
Yeah.
yeah.
No, I love error messages because they teach you a lot. So this says application type mismatch. Application is the process when you give arguments to functions. So here it's saying, look, string append is being applied to string append. Oh no, because string append takes type string, right? But the argument we're giving it, which is also string append, has a different type. It has the type string to string to string, right? That's not the same as the type string. So you can see that very clearly in this error message, right? It says that the argument has this type string to string to string, but it expected to have the type just regular old string, right? And so it's a mismatch in the arguments. And as you program in functional programming languages, it's important not to ignore these error messages because that's the only way you can basically figure out what you've done wrong in a lot of when you get into more complicated cases. So it's good practice to try to read these things and understand them.
Right. Yeah. And then usually the way I think of it is you do the brackets thing first. So this will
Yeah.
first, if I was working this out by hand, I would look at the stuff in the brackets.
Yeah.
And you sort of imagine it like a tree. Well, it's kind of similar to this kind of tree I drew before.
Yeah.
And then this would be like the inner thing, and then you work out this. This will be like the brackets, and then you can work out this using the answer from this and this.
Important thing is that everything inside those brackets gets evaluated first and then applied to string append. And since it's since string append returns a string when it gets its two arguments, then that whole thing inside the brackets will evaluate to a string, right? And so then it becomes a valid argument to string append.
Right. Because this thing I'm highlighting is going to give us a string. C is also a string. We're okay.
Yeah, and then we're okay. Yeah. Okay, next one.
All right. Oh, is this? This is your one now, Avi.
Okay.
The pressure's on you.
So, okay. So if 3 equals 3, then 5, else 7. And we're also learning here another operator, which is this double equals, which I guess is checking equality of value. Okay. So I'm going to say 3 is equal to 3. So that's true. So that's going to give me 5.
Right. That sounds reasonable to me.
Check it out. What do we got? 5. Yeah. And now let's just to check it, let's do 3 equals 4 and see what happens. So I can change.
Oh, that's the next one.
Oh, that's the next one.
You're doing my work for me. That's fine.
Okay, so fine. What is it going to be?
I think it's going to give us not equal.
Not equal. That's right. Well, should. Yeah. Okay, let's try it.
Yeah. Let's see. So, I mean, this is pretty analogous to before. I don't know if we need to explain. Yeah. I mean, because this is false, it's giving the second argument.
Okay, so I just, was showing we have this eval 1 plus 2, right? And we already showed this before, but let's just quickly show it again, right? If I do check, I can see the type of that. And so you want to put your cursor over that?
Yep, we've done this.
Yeah, okay. So now what if I do, though, what if I do check 1 minus 2? What do you think? Before you put your cursor, what do you think?
Oh, sorry, nat.
Oh, but that's weird, right? Because is 1 minus 2 a nat?
Oh, no, it isn't. That is weird.
Yeah, so something a bit strange. Well, okay, let's see what the textbook says. So it says, oh, I see. You got to, if we eval 1 minus 2, what does it do? We might even get an error. Oh, So what do we, oh, we get 0, right. So I think the way
Oh,
math work is
it's got bounded subtraction.
bounded subtraction, right. So it won't
Mm.
let you go below 0 because the default is that when you just put in like numbers with no decimal place, it interprets those as natural numbers, right? So so for those of you who, just for the listeners, right, a natural number in computer science terms is a whole number from 0 on up all the way,
0, 1, 2, 3, 4, and so
0,
on.
1, 2, 3, etc. Right? So if you go 1 minus 2, which if it was an integer would be -1, since it's a natural number, it can't be -1, so it has to be just capped at 0, or whatever the word for capped is on the bottom end of something.
Right. So like 5 minus 5 is 0. And we know that really 5 minus 6 is -1, but it thinks 5 minus
yeah
6 is 0 as
and
well.
you can see there, even if it's like -1,000 or something, it's always going to be 0, right? So
Yeah, that's
okay,
cool.
yeah, but one way we can actually do this is we can explicitly tell it the type that it should be, and we can do that using this colon and type in int, right? And now you can see that the value is -999.
Oh, that's interesting.
So so what we've done here is we've given it some additional information about the type, right? By default, it interprets those numbers as natural numbers. But if we tell it explicitly, hey, this should be an int, not a nat, right? We do that by putting this colon here and typing int.
It's kind of bothering me a bit that you're doing this to the answer. Like in a sense, I know it's maybe a bit pedantic, but I would have thought you'd go in and say, well, think of 1 as an integer, think of 1,000 as an integer, think of minus as a map that takes in a pair of integers and outputs an integer.
I mean,
But
you can do it this way too.
rather,
So there
the
I've
way that
done
you've
each.
wrote it is like work it out, in which case I would have thought it would just be like, oh, default mode, I'm working with naturals. And then, it would give the answer 0. And then it would be like, but 0 is an integer. You see what I mean?
Yeah. So do you see I've refactored it there? So you
Oh, and it
can
still
apply.
works.
It still
Right.
works. Yeah. So you can type each individual number as an int and then subtract them, but you can also subtract them and then type it as an int. But I think it doesn't do the calculation. Like it's still doing the type assignment before it does the evaluation. Because if it did the
Yeah.
evaluation first, the answer would still be 0,
But
right?
it's a bit weird that it sort of has this expression and then it has to somehow take the things inside the expression and turn them into integers. It's fine in this case, but I can imagine in more complex cases it being difficult to understand what it's doing.
So think of it as just like you're giving it a clue as to how these should be interpreted, and then it will just interpret them that way. But I agree with you. It's a little bit like it's an advanced feature, right? Like it's more for a programmer to not have to be so pedantic about like typing
Yeah.
every single value individually.
Right.
Yeah. Okay. So now we've seen how types actually matter for evaluation. They're not just sort of like extra, like in this case, and that's because like the way that subtraction works for an integer is different than the way subtraction works for a natural number. So even though we're using this same this same symbol, like the dash symbol we're using for subtraction, is actually corresponding to two different functions if we're using it for a natural number or for a integer, right? And that's
Mm-hmm.
kind of also happening behind the scenes, right? You wouldn't necessarily notice that just from looking at the syntax, right? But once you see how it evaluates, you can see, oh yeah, it's obviously doing something different because we're getting 999 minus 999, or we're getting 0, right?
Mm-hmm.
So obviously they must be different functions. So it's using the type information about the arguments, in this case, like that the arguments are natural numbers, or actually, sorry, that the answer is a natural number, to infer which like function it should use and which how to type the arguments of that function. So it's doing a lot of things behind the scenes.
Yeah. Got it.
Yeah. And I mean, basically, this is all to make this kind of type
So I guess
stuff more
the way it
flexible.
probably works is it's like I know now that the output's going to be an integer, so I should use the minus that works on integers. then I
Yeah.
know that the inputs that are minus should also be integers. So it kind of
Yeah,
works
yeah, yeah,
backwards.
exactly. It probably says like I look at all of the functions that I have defined for this minus symbol, and I find the one that outputs an integer,
Mm,
right? And then what are the arguments for that function? Oh, they're integers, right? So then it interprets these numbers as integers.
yeah, yeah.
Yeah, yeah. So that's very interesting what it's doing behind the scenes. And yeah, I wonder
So
what else.
did you say you have to go in like 10 minutes? Because I just saw how to define functions on things, so I wanted to say that before we have to wrap up. But
Yeah, let's
I
do
won't.
okay. So let's just do quickly create a new file. 01 dash 3 dash functions and definitions. Okay, so you can go ahead and open up that other file. So we're on section 1.3 now of the book.
Right. So I don't know if this is from book, but like, say we want to define something that's going to add one. So we'll call it add one. The input's called x, and then we say it's equal to, and then the output's going to be x plus 1. And so now let's test this. So we want to, oh, it's hash eval, isn't it? Hash eval. And let's try and add 1 to 7. Ah, and it works. We get 8.
Yeah.
So that's good.
So we kind of skipped over a few, well, that's fine. But before we go on to defining functions, just I wanted to point out like that you can use it just to define like static values as well, right?
Mm-hmm.
So here we've got def. So basically, like in other programming languages, like you sometimes will write like const or var or let, okay? And here we're using sort of def. And that's because like we're not defining like in functional programming languages, usually you can't like reassign variables. So we don't have like let. Well, there are actually, I think, usages for let and stuff. But for now, we just think of this as like defining a constant, right? So hello will always mean this string hello, right?
Mm-hmm.
And if I do eval hello, right, I should get, you want to move your cursor up there? Yeah, I should get that string hello.
With a capital H, yeah.
Yeah, exactly. Yeah, because I can put in an
Like
exclamation mark.
the way I think of it to sort of unify line 4 and line 8 is that we can think of like hello as like a function that has no inputs.
That's right. Yeah, it's a constant function, or a function with 0 arguments. Yeah, that's right. And so it's kind of weird to think of a string as a function, but you can think of it that way, right? It's a function that just always returns hello and doesn't take any arguments.
Yeah, yeah. Or we could make one that's like def and it's called G and it always equals 8.
Mm-hmm.
So if we do a val of G, we get 8. And so you could say G is a function that takes in no inputs and it always returns an 8. Now maybe we can see what kind of type it has. Oh, it just says it's of the type natural number, so
Yeah,
it's not thinking of it as a function because it doesn't have to, because it's just going to give a natural number and you don't have to give it an input. You
yeah,
could say it takes in no inputs
yeah.
in
You
a
can look at it
sense.
either way because
Yeah.
it doesn't make any difference to how it would behave.
Maybe we can have a look at add one. What's it think
Yeah.
add one does? So check add one. Oh, so that's taking in an x, which is a natural number, and outputting. And I just do one more because then we've got all the building blocks. So if we want to times two things together, this one takes in an x and a y, and it outputs x times y. So let's.
Now, what's nice about this is how similar this
Oh,
kind of
is it?
definition
Hang on,
is.
has it gone wrong? Maybe that? No? What's going on here?
Let's see, type class instant problem is stuck. It is often due to meta variables. Okay, so this is, what I would try doing is just typing the inputs, right? So it doesn't know, because times is defined for lots of different types. So we're thinking of these as natural numbers.
Oh, there. Right, I see. Got it, got it. Oh, hang on, it's still a bit confused. Ah, brilliant. Okay, so let's see if this works now. So if I go eval times 3 and 4, yeah, it works. Okay, yeah, go on, Abby.
Yeah. So okay, that kind of you somehow you've lost your word wrap again. So do you want to just do that? Control Shift P. Probably want to change this your setting somewhere so that it'll be on by default. But yeah. So and you can also make that like column a little wider to make it not wrap as much. Yeah. Okay. So okay, I think we didn't explain this super systematically. So just going back to the def hello, notice that when we're defining it, we use this colon then equals, right? And in math, sometimes you'll see that where people, when they're doing a definition, will use colon equals to mean like by definition, equal by definition, as opposed to asserting that two things are equal. Like if I say 2 plus 3 equals 5, that's not by definition, right? That's kind of a fact based on how addition works and how numbers work. But here we're saying hello is equal to the string hello, like just by definition, by fiat, right? And that's what that colon equals means, as opposed to the equals, like where you use the equal sign twice. And some languages will actually have the same symbol for the definitional equality and the other equality, which can get very confusing. So I think it's nice that they have different symbols. And then we have, and then in add, and then the other thing to explain is when we're doing this, like let's look down at the times here. What we're doing is basically we're pre-applying these arguments in the definition. So we're saying that times is a thing which when you apply x, which is of type nat, and y, which is of type nat, the result will be equal to x times y, where times is now like a predefined function, like built into Lean. But
So yeah, this times is like taking in two inputs, which are called x and y, and x has to be a natural number and y has to be a natural number, and then the output here is going to be x times y, which we also know is
and it will
a
infer.
natural
So
number.
let's do check times. Like
Oh yeah, let's see. So if we go hash check, whoops, I'm going to spell it correctly. Right, so it's telling us what it's doing. That's cool.
And it's also actually showing you a brief for syntax if you wanted to, for definitions. If you have multiple arguments of the same type, you can use
Right.
this kind of abbreviation where you do. So let's see if we can actually define it that way and have it work. Because it is a little annoying to have to type the nat twice every time. So yeah,
that should do the same thing.
Should do the same thing. Yeah.
Let's make sure. No, it's still 12. Yes, it does. Great.
Yeah. So that's a good way to like have a briefer syntax, although maybe a little bit less clear. So I think that's good for today. It was really great to go through these basics, and we'll build on these in future, right? Because
yeah, so we can put these blocks together to do different things, I suppose. So someone who's following along, they might want to see if they can make a function which times is by 2 if the input's bigger than 0, and otherwise it takes away 1, or something like this. There's all sorts of problems that one can pose oneself. Yeah, so any last remarks, Avi, on this one?
Well, it's really fun going through this with you, and like I think just always anytime you're discussing things with somebody, it kind of gets the knowledge in more deeply, because people always see things from different perspectives. So yeah, I think it's a great way to learn.
Yeah, so I guess next time, what's on the agenda, Abby?
Okay, well, we went through the first 3 sections of this book, and so I guess I would like to just keep going through the next section. So next we've got structures, is 1.4, data types, patterns, and recursion. So that's where I think we're really going to get into some of the fancier functional programming kind of stuff, like how do you actually do things, like, because in functional programming you don't have loops, for example. You don't have you do a lot of stuff with recursion that in other languages you would do with like a loop or something like that. So this is where we'll get into some, like, how do you, for example, like take a list of, like, let's say when we were looking at that string append, right, where it was just two arguments and we had to nest them, that seemed very kind of awkward, right? But the way you'd actually do that in functional programming is you would take a list of strings and you would fold that list using that string append function. So that basically iteratively says, like, take the first element of the list, apply string append to the next one, and then do that recursively. So you go through the whole list. So that's the kind of thing we'll learn to do next time, which lets you get into some more powerful programming.
Yeah, that's the really good stuff. That's where
Yeah.
like everything gets very interesting. Yeah.
Yeah. All
Awesome.
right.
All right then. Next time.
See you next time.
Bye bye.